Well, hi, Maddie. This is Mr. Brown from the Hun School contacting you. Just want to let you know that I haven't forgotten about you. And I was looking over some of these problems that you sent me. Thanks for sending these. So I just want to go through them with you really quick, just in case. Maybe there's a way that I'm explaining it that might be a little bit easier for you to understand, or just sometimes hearing it from a different voice makes things better. So hopefully the videos that I sent you earlier helped a little bit, but maybe this one can go on top of it and just be sort of the cherry on top of the sundae. If you need any more help, I can go over your quiz with you as well to get you ready for your upcoming test, which I hope you do really good on. I'm cheering for you. So here's what I'm looking at. I'm looking at these review problems that your teacher got you. And I asked you before if you are allowed to use calculator on these because I noticed when I started working on this first one that this one was actually kind of tough to solve and find all these things about by hand. So when we had the calculator, it's a little bit easier. But I think to help you really understand what the heck we're doing here in calculus, I think I'm going to show you both ways. And when I get stuck, we'll go over to the calculator and see how that will help us. But here is the gist. Okay, so you're trying to find all these important things about this function here, x times sine of x. And the first thing you usually want to find when you try to find anything is what are called the critical points. And the critical points for our function are where the derivative does two things. First of all, where does the derivative equal zero? What are the zeros of the derivative? Not the original per se, but of the derivative. Not only that, where is the derivative equal to zero, or where is it undefined? Undefined can happen a lot of times when you have, say, a fraction, and somewhere in the denominator, if it ever equals zero, which we don't like, we never want the denominator equal zero, right? That's bad. Whatever numbers make the denominator equal zero, that will make the derivative undefined. So those are also going to be critical values. So we'll try to find where is the derivative equal to zero and where is the derivative also undefined. Those will be our critical points or our critical values. Okay, so let's try to figure this out. So first of all, let's try to find the derivative. So given this function here, let's find what is capital F prime of x. Okay, what I'm looking at my function here, and I've noticed it's made up of two different friends here. I have x and I have sine of x. And what are they doing? They're multiplying each other. So I know that because they're multiplying, I'm going to have to use what's called the product rule. Okay, so just a quick review of product rule. Product rule says you're going to take the derivative of one of the friends, but keep the other friend, and then you add the switch. So we keep the first friend and we multiply by the derivative of the second friend. Okay, so derivative of 1 times just the regular other part plus, then you switch, then you keep the first part of the function and you take the derivative of the second part. Okay, so the derivative of x is just 1, so that's not too bad. So 1 times sine of x plus, okay, the x stays there, and the derivative of sine, if you remember your trig derivatives, is cosine of x. Okay, so my final derivative here is sine of x plus x cos of x. All right, that's f prime. Yay, congratulations. That's great. So what do we do with that? Well, to find our critical points up here, we need to set this equal to 0 and also find where's the undefined. But you know what? Because this is not a fraction, there's actually no values of x that are going to make that undefined. So I'm just going to skip the undefinedness right now and just find out where it's equal to 0. Normally, we could think about maybe factoring it, but there's nothing here that we can factor out of both pieces. So that's when I realized right away we're probably going to have to look at a graph. So I graph this on my calculator and I try to find where does my derivative equal to 0. And I got this pretty cool looking graph. I'll put it over here on the left-hand side. And from 0 to pi, which is where we're playing here, my graph kind of looks like this. And it stops right about there. And so that's my derivative, and I'm looking to see where's equal to 0. Well, right there, and then right here at the beginning. And I did realize by using some of the values on my calculator and some of the calc features, if you go like to the second button and go second trace, you get the calc button, and you can find that this value here is 0. That's one critical value. And the one over here is about, let's see, 2.029, 0.029, I believe. I know in our AP Calc class, we always use 3 decimal places when we round our answers. So I'm going to use 3 here just for you as well. Okay, so my critical values, my critical points are, final answer, x equals 0 and 2.029. And that's my final answer for A. Why? Because that's where my derivative equals 0 or undefined, but we didn't have to worry about undefined here. All right, that's the first one. Yay, part A is done. Okay, now for part B, we have to find all the extrema. Extrema means you want to find all the local maxes and all the local mins. And that just means within sort of a neighborhood of points, what are sort of the highest and lowest bumps? So for example, if I just made up this graph on the left, these little friends are sort of the highest in their little neighborhood of regions, so those would be local maxes. And this little bump down here in its little neighborhood of points, that is the lowest points, we call that a local min. So we need to find all the local mins and local maxes. The other type of max and mins are called absolutes, which we're going to do in part C, but that's not part B. Part B is just the locals. All right, well, normally what we could do is 2 different ways. If we could take our derivative up here and do what we call a sign chart on it, where we divide it up into different intervals and we check and see if it's positive or negative. I don't know if that rings any bells to you. That would tell us where the derivative is positive or negative, and then we would know that if I go from a positive derivative to a negative, that means I just passed over a local max. And similarly, if I went from a negative to a positive, that'd be passing over a local min. But here, again, we had trouble because this derivative is not very easy to find and solve for, so we're going to have to use the calculator for it. So I'm going to go back. I'm going to erase all this work that I did over here for you. Let's go back over here to what the actual graph looked like. All right, well, it looked like on our derivative here, let's see, we found one critical value at 0, but we can't determine if that's a local max or min because there's nothing to the left of it. Remember, we only took this interval from 0 to pi, so I don't know what's on the left of x equals 0. So I don't know if it's maybe, does it keep going and keep going downstairs like that? Or does it bounce back up again and make like a local min? We don't know. So because we can't figure out the left side of 0, I'm going to cross out 0. It's not going to be a local max or min. So the only friend that we're going to focus on is this one over here. When that one equals 0, that was at x equals 2.029, right? And remember, that's where the derivative is 0, so that's a critical point. But look what happened on our graph. Do you notice that you were going from above the axis to below the axis, meaning that's where your derivative was going from a positive to a negative. And we talked about if you went from a positive to negative, that would be a local max. So you could say your extrema would be a local max at x equals 2.029 because that's where the derivative was 0 and you were going from a positive to a negative. And that was the only zeros that we found on that graph of the derivative, again, from that interval from 0 to pi. All right, off to part C. Now we want to find the absolute max and absolute min. And again, we're going from 0 to pi. If we were doing this algebraically, again, we try to find our critical values first, or she calls them critical points. So what you do here is you take your critical points, which we said here were x equals 0 and x equals 2.029. Now, instead of doing a sign chart that we did up here, what we do is we take those values and we plug them back into the OG. We plug them back into the original function. And we try to figure out which x value is going to give me the highest y value and which one is going to give me the lowest. And that will give me my absolute max and absolute min. But we're not only going to plug in these 2 values of 0 and 2.029, but for absolutes, we also have to plug in the endpoints. Well, 0 is an endpoint. We're already going to plug it in over here, but so is pi. So now we have 1, 2, 3 values that we need to plug into our original function to see which one gives us the highest value. That would be our absolute max. And our lowest value would be our absolute min. So again, our game plan here is to take our critical values, and we're basically going to say capital F, the original, at 0 is, capital F at 2.029 is, and capital F of pi. So for absolute max and absolute min, you have to plug in your end points also. And we always plug them back into the original function up here. All right, well, we've got some really terrible numbers here and there, but some of them are not too bad. Let's see, if I do f of 0, that would be x times sine of x. All right, I'll make some space here for you, Miss Maddie. All right, well, the sine of 0, if you remember, is 0, and I'm multiplying by 0, so f of 0 is 0. All right, fine. Now, 2.029 is disgusting. I don't know how to plug that in by hand. I mean, except just literally write out 2.029 sine of 2.029. So I think I'm going to use calculator and cheat a little bit, because that's hard. But how about f of pi? Okay, that's going to be pi times the sine of pi. Now, pi is just pi, but I know that the sine of pi in my unit circle, again, is also 0. So 0 times pi is, again, 0. Okay, very exciting. So now I need to go into my calculator for a second. I'm going to plug in f of 2.029. So on my home screen on my calculator, as I'm talking to you, I'm literally plugging in 2.029 times the sine of 2.029. And also just make sure that your calculator is in radian mode, not degree mode, because we're usually in radians for calculus, because radians are more painful and calculus just hates kids. Haha. Here we go. I'm hitting enter. And I get that f of 2.029 is about, how about 1.8197? So how about 820 or so? All right, so we did all the great work. Now, the idea is our absolute max should be our highest answer, and our absolute min should be our lowest answer. And I look at these three numbers that I got out, and it looks like this number here, 1.820, is my highest y value. So that's going to be my local, sorry, not my local, Mr. Brown, my absolute max. And, ooh, I got two absolute mins. That's legal. That can happen. So if I say that those are both the same lowest number, those are both my absolute mins. Now, they say find the absolute max and absolute min, which means they actually do want the y values. So my absolute maximum is 0. You can say it's 0 at x equals 0 and 0 at x equals pi. And my absolute max would be 1.820 at 2.029. But your actual answer is the y value. Okay, so if we could do it algebraically, it's not too bad. But for part of them, especially this second answer, I had to use my calculator. Ew, gross. All right, increasing, decreasing. These are actually pretty easy if we can use our answers from part B. Because remember on part B, way over here on the right side, I said if we could use a sign chart, that will tell us local max and local mins really easy. And in doing that, you see how we made these signs here? I need a new color here, Mr. Brown. I had positive and positive, and I had a negative. Well, that tells you where the derivative is positive and negative. And remember, if a function's increasing, that means that's where the derivative is positive. And down here, if a function is decreasing, that's where its derivative is negative. So the sign chart actually tells us, it says, well, over here, if it was positive here and here, that means the original function was increasing. Well, fortunately, remember in part B, we couldn't use the sign chart because this was so hard algebraically to solve, right? We couldn't really do this one by hand, so we had to use the graph. So here's what we're going to do. Well, I know that the function is increasing where the derivative is positive. So if we can go back to, remember my graph over here, this was the graph of my derivative. Well, where's the derivative positive? Well, it's really everywhere where it's above the x-axis. So really this little purple piece right there, that's where I'm above the x-axis. And that is from x equals, let's see, 0 on the left. And where did it stop? Oh, well, that's got to be my 0, right? So 2.029. That's where my derivative is above the x-axis. That's where my derivative is positive. So that's where my original is increasing. Oops. 0.29. 9. There you go. So my original graph is increasing, my original function is increasing, where my derivative is positive. So I looked at the graph, I noticed that's where my graph of the derivative is literally above the x-axis. So where is it decreasing? Where is the derivative negative? Well, look at your graph. Can you see where the graph is below the x-axis over here? If the derivative is below the x-axis, the derivative is negative, so therefore it would be there. So how about from 2.029? And sometimes we would say until infinity, but I think your teacher was saying, let's use this restriction from 0 to pi there. So we'll cut it off at pi. That's where my derivative was negative, below the x-axis, and therefore that's where my original function is decreasing. So there you go. That's a very, very general, good question in calculus. And I hope that helped. I had to use the graphing calculator, which again, I hope is okay with your teacher as well. Okay, gonna take a little mental break for a second and come back and join us, and join us, join me. How many people are here, Maddie? Join me on number 2. All right, welcome back, and we're on number 2. Okay, same idea, find all extrema. Now, sometimes with different teachers, I'm looking at C right here on part B where it says find all extrema. Some teachers want you to find not just the local max and min, but maybe sometimes the absolute max and min. So how do you know what they're asking for? Do they want the absolute? Do they want the locals? Do they want both? Well, here's a good clue. Remember we said on the last page that when you do absolute max and min, you have to plug in the endpoints as well as the critical points or critical values. So you plug A back into your original. You plug B back in your original C. But do you notice that your teacher didn't give you any interval? So if there's no interval, how can you find absolutes? So they must mean only local max and min. Okay, so remember our steps. Let's find the critical points first. We'll set the derivative equal to 0 and also where it's undefined. If we can make a sign chart, great, or a sign graph, but it depends how easy this derivative is, or maybe we'll have to use the calculator. All right, so let's do it. Here is my original function, or your original function. So how about, let's see. Well, I think I could just use power rule here, but if it's okay with you, I'm going to change this friend over here to 6 times x to the, well, x is downstairs, right? And the thing that makes it downstairs is because it's raised to a negative power. So I'll call that 6x to the negative 1, if you don't mind. Let's call f deriv. Let's say that's, well, derivative of 2x is just 2. And then minus, well, the derivative of 6x to the negative 1. All right, power rule, that'd be negative 6x to the, let's subtract 1 from the power, negative 2. Or 2 plus 6 over x squared. All right, that's my derivative. Yay, good job. Now, to find criticals, let's set this equal to 0. We'll also check where it's undefined, and we do have a fraction here, right? So, maybe that's easier. Let's take a second, and let's just figure out what would make that undefined. Well, what would make that derivative, that denominator, equal to 0? And that would be when x equals 0. So x equals 0 is going to be one of our critical points, because it made my denominator 0, which means it made my derivative undefined. So he checks out. I'm going to use him. But where else is the entire derivative equal to 0? Come on over here. Let's figure it out. Let's set 2 plus 6 over x squared equal to 0. Ew, that's just gross. Okay, let's just move some furniture around. How about 6 over x squared equals negative 2? And I think I'm going to cross multiply a little bit here to free up the x squared. And I get x squared times negative 2. Okay, so how about negative 2x squared equals 6. Divide by negative 2, and x squared equals negative 3. Okay, now I know I'm going to take the square root, but can you see, looking into your future, I'm going to take the square root of a negative? Ew, gross. You can't do that. That's not a real number, right? That's an imaginary number. You can't take the square root of a negative. So I'm going to stop right there and say there's no value of x that's going to make my derivative equal 0. So there's no critical points other than this friend right here. That's my only critical point. All right. Well, what we can do is we can try to take a sign chart, and let's practice that. Let's practice a sign chart at 0. And if you remember, to do a sign chart, we want to pick a value to represent this interval and this interval. Because right now I've got two different intervals. Which one's going to be my answer? Well, I don't know. So let's try that. Let's pick a value to the left of 0. Let's pick a value to the right of 0. And we take these values, we're going to plug them back into our derivative here, f prime. And if I plug -1 in, I actually get a positive number back out. I don't know exactly what it is. It doesn't really matter. I just know it's going to be positive. And you know what? If I plug +1 into my derivative, I also get a positive. Remember what we said on the previous page? That means if my derivative is positive, my original function is increasing, right? Same thing over here. But wait, as I approach 0, do you notice that I go from a positive to a positive? I don't change signs. So guess what? There's no local max or min. So is there any extrema? No. So the answer for A is there's none. There's no local extrema, no local max and no local min. Huh. But interesting for part B. Do you notice that with our sign chart, if my derivative was positive, that means my original function is increasing. So I could say from -infinity, and we can say maybe all the way to +infinity, but 0 is not a good number because the original does not exist at 0. So I'm going to say from -infinity to 0 and 0 to infinity. And because the derivative here on the sign chart was never negative, it is never decreasing. And you know what? Watch, I'll show you. If you actually graph the original, it looks a little bit like this. And this. It makes sense that there's a vertical asymptote right down here at 0, because 0 is not in the domain. But do you notice now that there's no absolute max and min because it goes on forever? There's no local max or min because there's no bumps. There's no place where like it just stops and makes a bump up or down. Interesting. And finally, do you notice that as I travel left to right, the graph is always increasing? Even when I pass over 0, it's still always increasing. So these answers that we got make sense. It's always increasing. And extrema, there's none. What a tough problem. That's a really tricky one that he gave you, but that's a really good one. All right, so to review one more time. For part A, to find extrema, find your critical points by setting the derivative equal to 0 or undefined. If you can make a sign chart like we did here, that's great. Or if your teacher allows you to use a calculator, that's great too. And then increasing and decreasing, we got really well using the sign chart too. All right, we're on the home stretch. Number 3, I love these kind of problems, where if you're given the original function, can you sketch the graph of the derivative? And I love the notes you put over here, Maddie. These are really, really good and very, very helpful. And it's basically what I'm going to tell you too. If this is my original function here, the best place to start to graph the derivative is look for the bumps. I got a bump and I got a bump. And the reason why is, if you think about it, at a bump, what is the derivative at a bump? Meaning, if I drew a tangent line at those bumps, what is the slope of these green tangent lines? Do you notice that they're always equal to 0? Remember, slope is the same word as derivative. So I go for the bumps. If the derivative at a bump is 0, that means on my derivative graph, which I'm going to graph here in green, must have a y value of 0 because the derivative is equal to 0 over here as well. So I hit the bumps first, and the bumps tell me that's where my original has a bump. That's where my derivative is equal to 0. And then for the rest of them, I just think tangent lines everywhere. I think of the TLs, tangent lines. So as I work left to right, notice that my tangent lines here, if I just graph little tangent lines, they're pretty positive slopes. And remember, slope means derivative. So I'm going to draw y values that are in the positive land. And as I get closer to my value here at the green dot, which is like -1/2, notice that my slopes of my tangent lines are getting smaller, which is why my y values of my derivative are getting closer to 0. At the bump, remember we said the tangent line has a slope of 0. Afterwards, okay, let me erase some of these so I don't confuse you. Afterwards, notice that my tangent lines here have a slope that are negative. So it makes sense that my derivative now has y values that are negative below the x-axis. If I keep going, more tangent lines, more negative. Oops, let's put that in green, my bad. But look what happens after that. I start to sort of get tangent lines that are not quite as negative are starting to turn around a little bit. They're still negative, but like smaller negative. So do you believe that they're starting to go back up this way? They're still negative, but not as negative negative, which makes sense because once I hit the bump, remember my derivative, my slope is 0. So I head back up here and I hit 0. All right, after that, as I head up here to the right, my slope of the tangent lines are more positive. So my y values of my derivative become more positive. All right, let's erase all the yellows here. And can you see that my green derivative graph would look something a little bit like this? And that is indeed f prime. And it's just a sketch. It's not perfect, but we only want to try to find a sketch, and that's great. One thing we'll learn with normal polynomials, that generally your derivative will go down a degree or go down an exponent. This actually is a type of an x cubed graph, if you recognize that. And you notice that our derivative went down by 1. This is actually some type of parabola or x squared. And that's normally going to happen. So that's how you sketch a derivative. Go for the bumps, because the derivative at bumps are zeros. And then just draw tangent lines as you work left to right. And your tangent lines are your new y values. All right, the last is a good question relating to our MVT, or our mean value theorem. Basically, this says, if you're given a graph, maybe something like this, and I'm given some kind of interval. Here's from 1 to 2. So maybe from, say, here's 1 and here's 2. That the slope between those two values, meaning at 1 I have, say, a y value here, and at 2 I have a y value here. The slope between those 2 points, kind of like this, whatever that slope is, that there's got to be a c value, and c is x. There's some x equals c value somewhere between 1 and 2, where if I find the derivative, remember derivative is the same thing as the slope of the tangent line. There's got to be another tangent line somewhere between 1 and 2 that will have the same slope as this slope that we have here. Meaning, there's got to be a parallel line to my orange line. So if I imagine though, like imagine all these tangent slopes, there's got to be somewhere between 1 and 2 where the green tangent slope is going to equal the orange slope. And in fact, if you believe it, I'll draw it right about here. So this is going to be my c value. I just have to find it algebraically. But that's what the MVT means, that the sum slope between x1 and x2, the slope of those 2 points, that orange slope, there's got to be a parallel slope we find by using the derivative. So here's what we're going to do. We're actually going to simplify the right side using our equation, and then we're going to take the derivative over here and try to set that derivative equal to this value over here. So let me just do the left side first. The derivative of our function here, f prime, is just normal power rule. How about 3x squared minus 1? Okay, let that sit and chill. Now if we do the right side, if we do f of 2 minus f of 1, that's all the y values. So f of 2, if I plug 2 in, I get 2 cubed minus 2, that's 6, minus, if I plug in 1, I get 1 cubed minus 1, that's 0. I divide by 2 minus 1, which is 1. So the slope of my orange line is 6. It doesn't look like on the graph because I made up one for you. It actually looks like it's a negative slope. But here, for our purposes here, the right side should be equal 6. So we want to find what's the x value or c value where the derivative equals the slope on the right side. So we basically set 3x squared minus 1 equal to 6, and we solve. And I have just a short time left on this half-hour video, but basically you would solve for x. I think you get something really weird looking like the square root of 7 over 3. Let me fix that square root. It should be over the whole thing. And whether you need to put that in a calculator, I don't know. But I do know that because it's positive and negative, we only want the values from 1 to 2, right? So we can't take out the negative. That would not be in our interval. So the only answer would be x equals the square root of 7 over 3. I hope that helped a little bit, Maddie. I'll check this. I'll send this to you. And if you have more questions to get ready for your test, you just let me know. Have a really good day. Talk to you later.